All right, we're going to do diameter of a binary tree. Given the root of a binary tree, return the length of the diameter of the tree. The diameter of the binary tree is the length of the longest path between any two nodes in the tree. This path may or may not pass through the root. The length of a path between two nodes is represented by the number of edges between them. All right, so let's unpack what that means. It's a tree. It's a binary tree. It's not necessarily balanced. And so if we start here, let's say our root is at 2. The diameter is going to be 1, 2. Uh, yeah. And if we start at 1, the diameter is 1, 2, 3. We're looking for a return of 3 there. All right, so let's talk about how to approach this. Whenever you're dealing with trees, you should probably think recursion. Uh, the reason for that being, you tend to do the same thing on each node as if it was a root, and then from there you build up from there. Yeah, it's the general benefits of recursion lend themselves nicely to trees. So in this particular case, so the diameter is the max length, meaning, so for example, if we were to compute a diameter at some lower node, so say we're at some depth of recursion, and we're considering 2. Well, its diameter that it's going to come up with is 2. We can't just add that to the diameter that we get from 1. So we can't say it's like 2 plus 2, that's 4, and we want 3. Yeah, 2 plus 2 is 4. We want 3. So we need this max depth. And separately, we also need to compare the diameter itself. Or no, so max depth. And the key being that it doesn't necessarily pass through the root. So say there's a bunch of, say these two children are both very, very long, and it wouldn't make sense to include the root. You'd have many, many children here, many, many children here. The max diameter would go through 2, but not 1, the root. So what we need to calculate, the diameter, if this particular node with a root, what's the diameter below it? That separately, and compare it against the actual diameter, so left max depth and right max depth combined. So since we need 2 values, and I only want to write one recursive function, I'm going to write a separate struct. And I'm going to use a class because I think it's a little easier to remember just the one definition. Sometimes you're going to need classes, sometimes you're going to need structs, but they're almost the same. So really, just pick one. I can also never really remember if, like, for structs, if you need to write like struct again every time you actually declare a variable of one of those, or if you need to write like type def, or if you need to write like the name of the struct after. There's like some weird rules I can never get right. So I think it's better just to stick with the class. And the only difference between a class and a struct is that for classes, the members are private by default, and for structs, they're public by default. So if you just declare them public, it's the same. So I'm going to call it, I can't call it tree node because that'll be overridden. So I'm going to call it like ret, I don't know, type, I guess. Public. And it's going to have 2 things. They're both going to be integers. One of them I'm going to call, I'm going to use short labels, MD for max depth. And the other one I'm going to call diam for diameter. In production code, I would write out max depth and diameter like in full. But since this is an interview, I think it's better to keep the code small. So smaller variable names can help, as long as you keep them straight. They have to be clear what it is, but as long as you could just tell the interviewer what it is. So MD for max depth. I'm going to give them default values of 0. So for example, on a lower level of recursion, or if like the root is null, so if we're like recursing on a null value, or if the root itself is null, obviously there's no depth or diameter to it. So that makes sense. That's fine. Let's see. And Since our input is a pointer, we should check for null by default. That should just be like your go-to. I have been asked that in a Google interview in the past. I did pretty well on it, but I missed that, and he had to remind me at the end. I had gotten enough other things. I think he felt comfortable reminding me. So but that was something I had to be uh, reminded of externally. Anyway, when you have pointer inputs, check for null. So if not root, we're going to return 0. That would be a good default value. All right, what do we do next? I'm an advocate of the pattern generally of, say you've got some recursive function you want to write, just make a separate function. And that way this original one it'll only be set up. The purpose is to set it up and then call your other function. And that way you can give it the signature that you want that fits you best without having to like adapt a strict given signature to your needs. So this one is going to return the return type. And I'm just going to call it explore because it's kind of a depth first search bit, but it's not really depth first search. So I'm going to call it that. And it's going to take the same thing. It's going to take a tree node pointer. So let's think about what this does. Semicolon. It's got to, first of all, it's recursive, so we need a base case. If not root, same deal. I'm just gonna return just one of these. Just instantiate it and return it. I'm gonna remove these, make it a little more concise. For coding style, it is better to consistently use the braces every time, especially in production code. But I like to keep it smaller if possible. As long as you know for sure there's only going to be one statement executed after the condition, then or you could do something like this where it's on the same line. I don't know. Pick your poison. I don't like to have like super long functions where there's a ton of empty lines with just like a brace on it. At least in like interview settings. All right. So what do we do next? We got to do a couple things. Let's think about at the root first. What are we gonna do in this setup function? We need to call our function, this recursive one, on both the left and right children. So ret left equals explore root left, and same for the right. And then we have to return something. So what do we return? We're comparing two values, so it's a max. What are we putting in the max? There's this diameter, so diameter versus max depth. So this is the easiest one to think about. And all right, so a little syntax note. This max function in C++ it has a couple of signatures, but none of them have 3 values. So we're going to compare 3 values. We're going to compare the diameter that we got from the left child, the diameter we got from the right child, and a calculated diameter that uses the max depths of both the left and right children. So we need 3 inputs. A way around that without calling max a bunch of times is you use braces, and that resolves to, I think, a vector, it definitely resolves to just like an array of the data type that's in it. So as long as all the elements in it are the same data type, it'll resolve to an array, and it's syntactically more concise. I don't know what version of C++ that was introduced in, but LeetCode uses 2017, which does support it, I think. I think it's 2017. It does support it for sure. So we need left dot md, no, diam, right dot diam, and then the calculated value. So how do we calculate it? We've got these max depths that we're returning. So for we want it to be 3. So we're expecting a max depth of 2 to come back from the left and 1 to come back from the right. For sure on the right side, it's going to be a max depth of 1. That's what we want. So I'm going to expect that. So I'm going to do the sum of just the simple sum. So left dot max depth plus right dot max depth. Okay, now let's look at the explore function. We got our recursive base case. We got our base case because it's recursive. And we need to do something pretty similar. It's kind of almost the same. Not quite, but almost. Type. Oh my gosh. Type left equals explore left. And then the same thing to the right. All right, so what do we do here? It's going to be a little different. So let's declare our return type now. So return, I'm going to call it ret for return. And we have to set both of its values because we need both for the upper level calculations. The max depth, I think, is going to be kind of simple. So that's going to, okay, the max depth, it's going to be the greater of the left or right max depths plus 1. So max left dot max depth, right dot max depth plus 1. It's going to be 1 higher. So how's that going to work out? At 5, we're going to, so say we're here, we're going to call recursively on the left and right. Those are going to return max depth of 0. So then at 5, its max depth is going to return to be 1. And then at 2, same thing, it's going to return a max depth of 2. So 1's going to get back a max depth of 2 from here. And then similarly, 1 from here, because 3 is going to get 0 from its children. And then it's going to return 1. So 1's going to get 2 from here, 1 from there. That's what we want. Now, a little bit of like a tricky concept that took me not super long, but a little bit to get straight is we're not adding back a 1 in this upper setup call. So at the original root, we're not adding a 1. It's only in these recursive like child calls that we're adding a 1 to our max depth. And that is kind of what it needs to work out. Because obviously, like, we want our diameter to be the sum of the 2 depths, which is 2 plus 1, that's 3. As opposed, even though our max depth alone, if you would include the root, is 1, 2, 3. That is a chain of 3. It goes 3 down. But that's not what we want. We want to consider only the ones, the nodes below it. All right, now that I've explained that in excruciating detail, let's calculate the diameter. This one's going to be a little trickier, maybe, potentially. So it's going to be the max of what? I think it's going to be similar to this, because this is a diameter. This is a calculated diameter versus returned diameter. So we want to compare it against the returned diameters below it. So left.diam, right.diam, and we have that third value, which is calculated, which is going to be the sums. Do I need to add 1 to it? I don't think I do, because I don't think I need to add 1 to it. Let me think about that. I'll type it first and then think. So left dot max depth plus right dot max depth. All right. So we want, so we're say we're starting at 5. It's gonna return its children, the null children are gonna return a max depth of 0 each. So 0 plus 0, 5 is gonna get back a 0. So it's gonna return a max depth of 1 up to this node here, and it's gonna return a diameter of 0 plus 0. Those are the left and right calculations. And then The diameters are also going to be 0. So it's going to return a diameter of 0. So 2 is going to get 0 diameters from its children, which kind of makes sense because they're lone nodes. But its diameter that it's going to return is going to be calculated, and it's going to be the max depths, the sum of the max depths. So its diameter is going to be max depth of 1 that it gets back from here. The return to max depth, 1 and 1. So it's going to return a diameter of 2 because it's based on the max depth, which also makes sense because there's 2 edges below it. So that's what we want. Okay, that's the correct diameter if it's a simple sum. And then we got to return. Return ret. That might be it. So I'll talk about time and space complexity, and then yeah, I guess I'll step through an example. All right, so it's a binary. It's a tree. Obviously, if we have to search the whole thing, we're looking at a target runtime of at least linear. So the number of edges and the number of nodes, at least linear, which is that's in fact what we get. We don't call this recursive function more than once per node. We got a few extras on the null children, but that's all right. That doesn't change the algorithmic complexity. And it might even improve the, so calling on the null, I'm thinking about like esoteric constant time factors here. So if you call on the null, you do have to allocate a new stack frame, but you do nothing on the stack frame. Versus if you were to compare the null children and like see that they're null and then handle it before calling, then you're doing more conditional checks, but you don't have another stack frame. However, since we're riding under time pressure, I always recommend, if you can, check if the current node is null. Don't check if the children are null. That gives you just this one, it gives you fewer places to check for these conditions. The logic tends to be a little simpler. It's a little cleaner, and also it's fewer lines of code, which is important when you're typing under time pressure. Okay, so it's linear. So yeah, what do? We do that's constant work. This whole thing is constant work. Oops, not including the recursive call. When you're dealing with recursion, there are some like theorems you can use. There's one called the master theorem. I can never remember it. It's easier, I think, just to like step through and derive your runtime. Don't. So this is always 3 items. So this is constant work for the max call here. And then for each of the children, so we're definitely calling once per child, once per node overall. We're doing this. This is a constant check. The recursive calls. And then, okay, so here's the actual work. This is a max comparison and addition. And then this is just another max comparison over always 3 items. So these are both constant. And as with all runtimes, technically it's going into the weeds here, it's linear on the number of bits, but since we're dealing with a constant number of bits, then that makes it constant. So this is constant work per step here, meaning that the only non-constant element is the recursive calls. And we're doing 1 per node because there's no cycles. That's not an issue. All right. And then space, so it's O of, I'm going to use this syntax V. So V is the set of vertices, and the bars means the size of the set of vertices. Technically, it's this, where E is the set of edges. But since it's a tree, that means there's always, particularly it's a binary tree. So there's 1 fewer edges than total of nodes. So 1, 2, 3, 4. There's 4 edges, 5 nodes. You can erase this. You can erase the V either one. Because they're the same order of magnitude together. So it's really this time and space complexity. Since we're doing one, let's see. Yeah, we're doing 1 stack frame per node. And it looks like that's it. It's all constant space because we're tracking like this structure, which is 2 integers. So 4 integers there, another 4 integers per stack frame there. And that's it. So it's constant space per node. So it's linear space overall. Think about if you've got a big line, say every single node is just like down the left or something, so all 5 nodes are just like in a diagonal. You'd end up with all of them in the stack frames at once. So then you've got linear time and space. All right, now that I've beat that to death, yeah, let's rush through an example. I don't know if it needs to be crazy. So okay, this is gonna be our stack. First, we check if the stack is null. It is not. So then we're going to explore the left child, and I'm going to put 1 on the stack. So now we're at 2, and we're down here. So same thing, we check if it's null, and then we keep going down to the left. So 2 and then 4. So now we're at 4, and we call on its left child. That one is null, so we're going to return this with a diameter and max depth of 0. All right, so then left and right child, those are both. So okay, back to the 4 node. So I'm gonna keep that unwritten down for now. So we're at 4. It's got back zeros. And then, okay, so we have this return type, max depth 0, 0 plus 0, 1. So it's going to return a max depth of 1. And this is also going to be 0 versus 0 versus 0. So it's going to return back to 2. So 2 has got a max depth of 1 and a diameter of 0. That's what it got from the left. And then so now it's going to call into the right child. And it's going to get the same thing back. You can see 4 and 5 are pretty similar. So it's also going to get another 1 and a 0 from its right child. So then 2, when it does its calculation here, it is going to, what's it going to do? Max depth. So 1, 1, 1 versus 1. Those are both going to be, so 1, that's 2. It's gonna return a max depth of 2 and a diameter of 0 versus 0 versus 1, 1, and 2. Yeah, so it's going to return a diameter of 0 and a max depth, diameter of 2, max depth of 2 from this 2 node. So we're going to pop that off. We're going to go back to 1. So 1 has now got 2's from its left child. So now we descend into the right child. So this, we're at 3. We're going to see that when 3, so 3, it's going to send to the right child. So now we're here for the 1 call. 3 is going to come to the top. We're going to see that's not null. And it's going to descend into its left child. The left child is going to return 0s. Then it's going to descend into its right child. The right child is going to return 0s. So then the 3 itself is going to return 0 versus 0 plus 1. And then it's gonna be similar to what the 4 and 5 returned. So it's gonna return 1 there and a diameter of 0. So 1 is gonna get back from its right child a max depth of 1 and a diameter of 0. Wait, sorry. The max depth. No, sorry, it's gonna return 1s because 3. No, 3's max depth 0 plus 0. No, it's gonna be 0s. All right, so no 1s, back up to 1. And I think we break out of this now. Next. Okay, we're back up to, we finally exited out of here, and now we're at here. So the left diameter, which is this value here, 2, versus the right diameter, which is 0. So there's no, that means, so 2 versus 0. So there is a diameter of 2 down here. So this 2 is referring to these 2, which does not go through the root. However, the calculated diameter would go through the root. So that's going to be the max depth of the left and right combined. So it's this 2 and 1. So the 2 here, this max depth is referring to this. This 1 is referring to this. And so the calculated value is going to be our output. So then we're going to return 3. And that's it. And let's see. I don't know what this would look like exactly. I'm not sure how it translates the arrays into like an actual tree. Well, so it looks like the node left and right child. And then, okay, it's in like reading order. So 1, 2, 3, 4, 5. Yeah. So this would be 1, and then a left child of 2. So it's just like a single node. It's just this. This is what that is. These two nodes here. And of course, that's going to have a diameter of 1 because it has a max depth of 1. Yeah, that makes sense. Okay, I'm convinced. Let's go ahead and give it a run for syntax. Come on. Don't fail me now. Boom. All right, and submit. Cool, cool. All right, so diameter of a binary tree, mark it off, and you have a beautiful evening.